Integration of logarithmic and inverse trigonometric functions. Okay, so let's move on to a new topic, integrating logarithmic and inverse trigonometric functions. Now, remember in the sections we covered earlier on integration by parts, we established that choosing the right functions to call f of x and g of x is absolutely crucial for making the process work smoothly. It's not just about plugging into a formula, it's about strategy. This slide highlights that some functions aren't as straightforward as others when it comes to integration by parts. Specifically, we're talking about logarithmic functions, like the natural logarithm of x, and inverse trigonometric functions, things like sine inverse x or tangent inverse x. These functions behave a little differently. The reason they're tricky is that while it's usually easy to find their derivatives, that is, how their values change, finding their antiderivatives, or integrals, directly can be quite difficult. We'll see in the following slides why this is the case, and more importantly, how to overcome this challenge. We'll be learning a specific technique to handle these types of integrals effectively. So, keep this in mind as we proceed. These functions require a slightly different approach. The conceptual challenge. First, let's look at the integration by parts formula itself. It states that the integral of the product of two functions, f of x and g of x, with respect to x, is equal to f of x multiplied by the integral of g of x, minus the integral of the product of the derivative of f of x and the integral of g of x. With respect to x, it looks a bit complicated written out, but the key is understanding how the parts interact. Now, remember that with integration by parts, we need to integrate one of the functions and differentiate the other. The success of this method hinges on making the right choice. This slide points out that while it's relatively straightforward to differentiate functions like the natural logarithm of x, which we'd say as log x, or the inverse sine of x, which is arc sin x, finding their antiderivatives or indefinite integrals directly is often difficult. We don't have simple, memorized rules for those. And this is where the problem arises. If we were to choose a logarithmic or inverse trigonometric function as our g of x, the function we intend to integrate, we'd run into trouble. Because, as we just established, finding the integral of g of x, in this case a log or arcsin function, isn't easy. It would lead us down a complicated path or even a dead end. Okay, let's move on to slide 2. As we discussed on the previous slide, integration by parts is a powerful technique, but it requires careful planning. This slide highlights why integrating logarithmic and inverse trigonometric functions can be tricky, and sets up the strategy we'll use to overcome those challenges. So, this slide is essentially laying out the problem. These functions are hard to integrate directly, and choosing them as the function to integrate within integration by parts won't work. The next slide will reveal the clever strategy we use to sidestep this issue. The strategy, the hidden one technique. This slide outlines how we do that. The first key idea is to treat the logarithmic or inverse trigonometric function, things like log x or sine inverse x, as our first function, which we're calling f of x. Why? Because, as you know, differentiating these functions is actually quite easy. Remember, the goal of integration by parts is to shift the integration to a simpler part of the expression, and these functions have simple derivatives. Next, we introduce a constant function, simply the number 1, as our second function, g of x. This might seem strange at first, but it's a crucial step. It satisfies the requirements of the integration by parts formula, and more importantly, it simplifies things dramatically. Let's look at an example to illustrate. If we want to integrate log x, we rewrite the integral as the integral of log x multiplied by 1. So, integral of log x dx becomes integral of log x times 1 dx. We're not changing the value of the integral, just rewriting it in a form that allows us to apply integration by parts effectively. And here's the beautiful part. With g of x equal to 1, the integral of g of x is simply x. The integral of 1 with respect to x is x. This is a very easy integral to compute, and that's exactly what we want. We've successfully set up the problem so that one part of the integration by parts formula is straightforward. Okay, so let's move on to the core strategy for tackling these types of integration problems. As we discussed on the previous slide, directly integrating logarithmic or inverse trigonometric functions can be tricky. But we can cleverly use integration by parts to make it manageable. We'll see how this all comes together in the next few slides with detailed examples, where we'll walk through the complete process step by step. But this slide lays out the fundamental strategy, the hidden one technique, that will allow us to integrate these otherwise difficult functions. Step-by-step example 1, integrating \log x $. Okay, let's work through a concrete example of integration by parts. Specifically integrating the natural logarithm of x, this slide breaks down the process step by step, building on what we discussed earlier about the challenges with logarithmic and inverse trigonometric functions. Remember, the key is that hidden one technique we talked about. Step 1, identify functions. As we decided, we're going to treat the logarithmic function as our f of x. So, f of x equals log x, and to make things work nicely, we're setting g of x equal to 1. This is where that hidden one comes in. It simplifies the integration process. Step 2, find derivatives and integrals. Now, we need to find the derivative of f of x, which is log x. The derivative of log x is simply 1 over x, and the integral of g of x, which is 1, is just x. These are relatively straightforward calculations, and that's why we chose to make g of x equal to 1. Step 3, apply integration by parts formula. This is where we put the formula into. Recall the integration by parts formula. The integral of f of x times g of x dx equals f of x times the integral of g of x dx, minus the integral of f prime of x times the integral of g of x dx. Applying this to our problem, the integral of log x times 1 dx equals log x multiplied by x, minus the integral of 1 over x multiplied by x dx. Step 4, simplify the expression inside the integral. Now, let's simplify. Inside the second integral, we have 1 over x multiplied by x. Notice that the x terms cancel each other out, leaving us with just 1. So, the integral of log x dx equals x times log x minus the integral of 1 dx. Step 5, perform final integration and add constancy. Finally, we integrate 1 with respect to x, which gives us x. Therefore, the integral of log x dx equals x log x minus x, plus the constant of integration. See, we can also rewrite this as x multiplied by the quantity log x minus 1, plus c, and there you have it. We've successfully integrated log x using integration by parts. This example illustrates how the hidden one technique transforms a potentially difficult integral into a manageable one. We'll see a similar approach in the next example with the inverse tangent function, and then we'll look at some real-world applications of these integrals. Remember to pay attention to the common mistakes we'll discuss later, as they often trip students up. Step-by-step example 2, integrating \tan minus 1 x $. Step 1, identify functions. As before, we need to strategically choose our f of x and g of x. Here, we're going to set f of x equal to arctan of x, or the inverse tangent of x, and following our strategy, we'll set g of x equal to 1. Remember, the goal is to make the integral of g of x simple, and that's exactly what we've done. Step 2, find derivatives and integrals. Now, let's find the derivative of f of x and the integral of g of x. The derivative of arctan of x is 1 over 1 plus x squared, and the integral of 1 with respect to x is simply x. Keep these results in mind, as they'll be crucial in the next step. Step 3, apply integration by parts formula. This is where we put everything together. Recall the integration by parts formula. The integral of f of x times g of x dx equals f of x times the integral of g of x dx minus the integral of f prime of x times the integral of g of x dx. Applying this to our problem, the integral of arctan of x times 1 dx equals arctan of x multiplied by x minus the integral of x times 1 over 1 plus x squared dx. We can simplify this to the integral of arctan of x dx equals x times arctan of x minus the integral of x divided by 1 plus x squared dx. Step 4. Solve the remaining integral. Now we're left with a single integral to solve, the integral of x divided by 1 plus x squared dx. This is where a simple substitution will come in handy. Let's set u equal to 1 plus x squared. This means that the derivative of u with respect to x, or do, is equal to 2x dx. We can rearrange this to say that x dx is equal to 1/2 do. Now we can substitute these into our integral. The integral of x divided by 1 plus x squared dx becomes 1/2 times the integral of 1 over u do. The integral of 1 over u do is the natural logarithm of the absolute value of u, so we have 1/2 times the natural logarithm of the absolute value of u. Finally, substitute back u equals 1 plus x squared, giving us 1/2 times the natural logarithm of 1 plus x squared. Step 5. Combine the results. We've now solved all the pieces of the puzzle. Putting it all together, the integral of arctan of x dx equals x times arctan of x minus 1/2 times the natural logarithm of 1 plus x squared plus our constant of integration, c, and there you have it. We've successfully integrated arctan of x using the hidden one technique and integration by parts. Remember to always include that constant of integration, c, as it represents the family of all possible antiderivatives. Okay, let's move on to our second example, where we'll integrate the inverse tangent of x. Written as arctan of x, this will further solidify our understanding of the hidden one technique we discussed. This example, like the previous one with log x, demonstrates how this technique transforms a seemingly complex integral into a manageable one. We'll be looking at some real-world applications of these integrals on the next slide, so you can see where this knowledge is used in practice. Real-world application context. Okay, let's move on to slide 6. Now that we've learned how to integrate logarithmic and inverse trigonometric functions using integration by parts and our hidden one technique, it's important to understand why we bother learning this. This slide highlights the real-world applications of these integrals. These integrals appear in physics and engineering. So, this isn't just abstract math. These techniques are essential tools used by professionals in various fields. In thermodynamics, entropy calculations often involve integrating logarithmic functions. Now, thermodynamics is the study of heat and energy. Entropy, a key concept in this field, often requires us to calculate the total change in a system, and frequently, that calculation involves finding the integral of a logarithmic function. Think of it like needing to sum up infinitely small changes. Integration is the perfect tool for that. In signal processing, inverse trigonometric functions describe phase shifts in waveforms. Signal processing is all about analyzing and manipulating signals, things like audio, radio waves, or even images. Waveforms, which represent these signals, can experience phase shifts, and inverse trigonometric functions, like arctangent or arcsine, are used to mathematically describe and analyze these shifts. Mastering the hidden one technique helps scientists find total accumulation of these quantities over time. Essentially, integration, and specifically this technique, allows scientists and engineers to determine the total amount of something that's changing over a period of time. Whether it's the total energy change, the total phase shift, or any other accumulated quantity, these integrals provide the means to calculate it. Now, keep in mind that on the next slide, we'll be discussing common mistakes students make when tackling these types of integrals. So, it's good to have a solid understanding of why we're doing this, as it will help you remember the correct approach and avoid those pitfalls. Common mistakes to avoid. 1. Incorrect selection of f(x). The first mistake we see here is choosing the wrong function to be f of x and g of x. A lot of students, when they first see an integral with a logarithmic function like log x, instinctively want to make that the g of x. But remember what we discussed, the whole point of our hidden one technique? If you set g of x equal to log x, you're left needing to integrate log x, which is exactly what we're trying to do in the first place. It creates a circular problem. we strategically choose to make the logarithmic or inverse trigonometric function f of x, so we can easily find its derivative and then pair it with a simple g of x, which is just 1. 2. Forgetting the 1. This one seems simple, but it's surprisingly common. It's easy to get caught up in the formula and forget that we're intentionally multiplying by 1. Remember, we rewrite the integral, for example, the integral of log x, as the integral of log x times 1. Explicitly writing that 1 helps you keep track of everything within the integration by parts formula and ensures you don't miss a crucial step. It maintains the structure and clarity of the process. 3. Sign errors. Now, this is a classic mistake in any integration by parts problem, but it's worth emphasizing here. The integration by parts formula has a minus sign in front of the second integral. It's incredibly easy to accidentally change that minus sign to a plus sign. Always double-check your sign. A wrong sign will lead to a completely incorrect answer. Be meticulous when copying the formula. 4. Omitting the constant c. Finally, and this is a general rule for all indefinite integrals, don't forget to add the constant of integration, c. The derivative of a constant is 0, so when we reverse that process to find the integral, there could have been a constant term that disappeared during differentiation. C represents that unknown constant. Leaving it out means your answer is incomplete. Okay, let's move on to slide 7. This slide highlights some common pitfalls students often encounter when tackling these integration problems, specifically when using integration by parts with logarithmic and inverse trigonometric functions. Paying attention to these will save you a lot of frustration. So, keep these 4 points in mind as you practice. Avoiding these common mistakes will significantly improve your accuracy and confidence when integrating logarithmic and inverse trigonometric functions. Now, let's move on to the final slide, where we'll summarize the key takeaways from this entire section. Key takeaways. Okay, let's recap everything we've covered regarding integrating logarithmic and inverse trigonometric functions. This is our final slide, summarizing the key takeaways. So, to begin the problem, as we discussed at the start, functions like logarithms and inverse trigonometric functions, things like log x or arcs in x, are relatively straightforward to differentiate, meaning to find their derivatives. However, when it comes to integration, finding the antiderivative, they present a challenge if we try to tackle them directly. They don't fall into any of our standard integration rules immediately. Now, the solution? The trick, as we've demonstrated, is to cleverly use integration by parts. And the key is how we set up our functions. We treat the logarithmic or inverse trigonometric function as our first function, which we denote as f of x, and we pair it with a constant function, specifically g of x equals 1. This might seem odd at first, but it unlocks the solution. Let's break down the process step by step. First, we set f of x to be the function we're trying to integrate, the log x or arcs in x, and we set g of x equal to 1. Next, we apply the integration by parts formula. Remember the formula? The integral of f of x times g of x dx is equal to f of x times the integral of g of x dx, minus the integral of f prime of x times the integral of g of x dx. In our case, since g of x is just 1, this simplifies to the integral of f of x times 1 dx equals f of x times x, minus the integral of f prime of x times x dx. Then, we simplify that expression and solve the resulting integral. Often, this new integral will be much easier to handle because it involves the derivative of our original function, f prime of x, which we can usually find easily. Finally, and this is crucial, the result. This entire process transforms what initially seemed like a difficult integration problem into one that involves finding the integral of the derivative of the original function. This is a huge win because integration and differentiation are essentially inverse operations. It allows us to proceed and find a solution, and don't forget to add your constant of integration, c, at the end. Remember, this hidden one technique is a powerful tool for handling these types of integrals. It's all about strategic setup within the integration by parts framework. And as we saw in the real-world application slide, these types of integrals show up in many areas of science and engineering, so mastering this technique is really valuable.